I do want to acknowledge I do this with a team of people. Dominique Bachelet from Oregon State now directs the Global Change Research Program for the Nature Conservancy in Washington, D.C. And Jim Lenahan works with me at the Forest Service and built the fire model that is embedded in the dynamic general vegetation model that I'm going to show you a bit about today. So without further ado, let's, like Linda, I want to give you a little bit of a pre-say of what we're talking about. And one of the key words I'm going to keep coming back to over and over again is this question of uncertainty. And Linda touched on it a great deal, and I'm going to keep hammering that nail over and over. And that is effectively that the future will no longer echo the past. And that uncertainty simply is never going to go away, no matter how good our models get it. So I'm going to go through a little bit of a hierarchy of assessments first. I'm going to talk a little bit about global scales and bring it down to local scales. And we're going to talk about time scales of variability a little bit as well. And this concept of natural climate variability, near-term and long-term trends, and the whole business of fire suppression is going to come in. And then some of the issues of concern that we're going to try and address at all of these scales will be things like vegetation type and species distribution and global carbon balance. Are we pulling carbon out of the atmosphere and putting it into the biosphere, or the other way around? And just as an aside on that, there is a couple climate model experiment going on that intercompares global dynamic vegetation models that are actually coupled with general circulation models of the atmosphere. And what they pretty much universally seem to be finding is that when you couple the biosphere to the atmosphere, it tends to produce a positive feedback effect. And that is that the biosphere releases more carbon than it takes up, and so the CO2 concentration in the atmosphere goes up a little higher and you get warmer temperatures. So then we're also going to talk a bit about fire and catastrophic disturbance, and just to hammer again on this business that we have all of our natural resource management, I don't care if it's water, wildlife, forests, or what, have been brought up in a worldview philosophy of effectively managing for the status quo. That is, we have things like historic range of variability, future desired condition. We know precisely what the site index is on any given chunk of land and what successional trajectory it will go through, and so on and so forth. And frankly, right now, I think that's all off the table. It's not useless. There's a lot of information there that we can use to help guide us into the future, and we can window certain pathways in the future. But we're never going to have that level of certainty that we thought we had about what that future is really going to be. And then the other thing is that things are changing really fast right now, and the rate of change is going to continue for a long time. And so in that sense, we have to manage for change. Instead of managing for a given condition, we're managing the process of change itself. And that's a different concept that we need to think about in terms of our goals and how we go about doing things. So this is output from a global dynamic general vegetation model. Now what that means is that it couples the ability to move vegetation around. We're not moving species around, we're moving plant functional types like evergreen needle-leaf tree, broadleaf deciduous shrub or tree, and grasses. And we compete grasses and trees for light, water, and moisture in these things. And we do it at every point, that is every grid cell on the map, independently from every other grid cell. And so you give it soils, a map of soils, and you give it a time series of climate month by month, and the model decides all by itself what will live there, what the vegetation will look like. And so when you see lines drawn on these maps separating different biotic zones, those are entirely emergent properties of the model. They're not drawn by correlations of climate with vegetation. They simply pop out. And so that's what moves around then when we alter the climate. And so this is global half-degree simulation. It's not perfectly accurate, but it's not bad. When we built the model, we actually built it on a landscape at Wind Cave National Park at a 50-meter resolution. All of the processes in this model are really plot-scale processes. And so we scaled that up and through some pretty coarse averaging techniques that we won't spend too much time on. And then here's Washington at a 2.5-minute resolution. That's roughly 4 to 5 kilometers. So what we want is one consistent body of theory that runs through the whole hierarchy of scales. Now, this doesn't show up very well. The red line is the same in all three of these. Showing behind it is a gray zone that shows a band of uncertainty. And this band of uncertainty is output from a bunch of different simulations from a single global climate model, starting with slightly different initial conditions. It's what they call an ensemble. And so it says, well, all right, given unknowns about the climate system, that gray zone bounds the uncertainty. So what they did here is include natural variability in the climate, the solar variability, and things like that. Here they only included greenhouse gas changes. When you don't include greenhouse gas changes, you do get this hump of change in the middle of the century, but you miss the heating at the end of the century. When you throw in just the greenhouse gases, you get the heating at the end of the century, but you miss the hump in the middle of the century. You put it all together, and you get a pretty decent simulation from a general circulation model of the past 100 years of historical climate, combining both the forces of natural variability and greenhouse gas forcing. So it's a non-issue, really, to say that it's either or, it's both. And one of the problems we run into is when we want to forecast out 5 to 10 years, which is what everybody kind of looking out, then we have this band of uncertainty to deal with. And I'm going to come back to that. It's in many ways easier to forecast out 100 years than it is 10 years. Because 100 years, your trends are driven by greenhouse gas changes, but over 10 years, your trends are driven by things like El Nino, La Nina kinds of oscillations. So here's how they build future scenarios. They trap a bunch of folks in a room and have them brainstorm what future societies would look like. Are you going to have a high population density or a low population density? Is their world philosophy going to be green earth, or is it going to be just spend carbon like mad? And so if it's business as usual, the CO2 emissions follow this high-end trajectory. If the world gets smart and says, well, we're going to try and control it, it might be this low end, this B1 thing, which winds up with a CO2 concentration that stabilizes at 550 parts per million. If you're somewhere in between, you follow this A1B, and it would stabilize at around 750 parts per million. That's about double today's CO2 concentration. Remember, we're already higher than we have been for the last several million years, very likely. This is sulfate. I'm not going to talk about that. So you get different CO2 concentrations that emanate from these scenarios. Now, if you put those together and run them into different general circulation models, you get this famed hockey stick curve. The past 1,000 years is from tree rings and things like that. And if you were to burrow deep into these uncertainties, you'd actually find the medieval warm period and the Little Ice Age. And that's all actually in there. Between the dashed lines is that 100 years of observed climate that I showed you in the previous graph of red lines. And so here's the hump in the middle, 30 years of cooling between the 40s and the 70s. But look at the slope of the curve from the mid-70s to the present. It's no different than the slope of the curve that's being forecast for the next 100 years. We're on it, folks. We've been on this train for 30 years at least in terms of rapid change. And this is the pace that is being forecast to continue. A little uncertainty on the slope of this line, and we wind up at the low end of change, which is roughly the magnitude of that middle Holocene thermal maximum that, that we heard in the previous talks. And at that time, vegetation zones were in the middle, in the Great Basin, had sometimes shifted 250 miles north of where they are right now. That's at the low end of warming. Robin Tausch talked about that. At the high end of warming, this magnitude up in here is roughly equivalent with a glacial interglacial cycle, the full swing, which normally takes tens of thousands of years. And we're talking about hammering this into 100 years. I mean, that's incomprehensible to me, and I've been studying this for a long time. This is kind of what they look like. If you remember that there was uncertainty among the GCMs. See, these are these three scenarios I singled out, the A2, A1B, and B1. And these bars show the differences among the different general circulation models. And so let's just look at a few of those. So these are two different general circulation models here. This is Australian, this is Japanese, and this is the high emissions, intermediate, and low emissions. But take note that the global temperatures at the high emissions of this model are very similar to the global temperatures at the low emissions of this model. So there's a lot of uncertainty in this, and this is in degrees Celsius. And as we heard earlier, it gets hotter at the high latitudes in this simulation. Rainfall, when you heat up the planet, you evaporate more water. You don't really change the storm tracks very much, but you do tend to shift them north a bit. And so it's like pointing a fire hose at the northern latitudes. So these blue areas show big increases in rainfall at the higher northern latitudes in both of these models. And they also show some drying in the middle latitudes, the tropical latitudes, particularly around the Mediterranean. And many of them show drying in the Amazon region as well. The transition zone between the wet zone and the dry zone is one of uncertainty, and that happens to be right where we are in the United States, with the exception that most of the models have at least the northern half of the Great Basin and the Northwest getting wetter. The southern half, sometimes it gets wetter in some of these simulations, sometimes it doesn't. The simulations don't do very well with the Arizona monsoon, but they're getting better, and the models that do it better show the Arizona monsoon strengthening. And so you do get more summer rains coming up out of these models. So let's just take a quick peek at the global assessments, just to show you that I'm not alone with our model. We have one of my best friends and also friendly competitors, Colin Prentice's group, with a model called LPJ for Lund, Potsdam, Jena, the cities within which they worked to develop this. They cranked 16 scenarios through that all came out with a temperature greater than 3 degrees by the end of the century. And they simulated change in carbon for the previous 100 years, that is the 20th century and the 21st century. And the gray zone is just the uncertainties around these 16 scenarios. So down means pulling carbon into the biosphere, and up means pushing carbon out of the biosphere. And so they simulate the carbon, in fact, should be coming into the biosphere, and the satellites agree with that. The satellites over the last 20 years actually show the world greening up. And there are various good reasons that we think that should happen, partly involving elevated CO2 concentration itself. As Robin pointed out earlier, and I think Linda did too, when you expose plants to elevated CO2, they respond quite dramatically. You can get an increase in the water use efficiency, which means you can put on the same amount of carbon for less water, or put on more carbon for the same amount of water, or anything in between. And so it does factor in. But what we do figure is that later on, as temperatures continue to increase, there's an exponential effect of temperature on evapotranspiration. And eventually that overwhelms even the extra water efficiency that you get from CO2, and the increased rainfall can be overwhelmed by the evaporative demand of exponential increases in temperature. Our model does the same thing. This is only the last 100 years, that is the 21st century, through 3 different climate scenarios, and we're showing the same thing. First greening up and then browning down. We call this sort of an early green up, later brown down. Now the concern here from a management perspective is that we become complacent. We see, hey, green world, wonderful, more productivity, more biomass, and then suddenly we hit that tipping point where the evaporative demand gets extreme and the system just crashes. And it can crash right out from under you fairly rapidly if you're not careful. I don't want to spend too much time on this slide other than to point out that, again, my friendly competitor, this is what we were looking at globally. This is his greater than 3 degrees set of scenarios. And he also had a bunch of scenarios between 2 and 3 degrees and a bunch less than 2 degrees. And he looked at risks of increased runoff in blue or decreased runoff in red. Likewise with fire, increased fire in red or decreased fire in green. And he also looked at conversion of forest to non-forest, which I'll show you a little better in a more close-up map later on. But green is increasing forest, and blue, in this case, is conversion of forest to non-forest. Looking at our model, this is just one simulation of a future climate effect, and it's the increase in fire across the world. I think it's the last 50 years of the 21st century compared to the last 50 years of this century in percent change in biomass consumed by fire. And you see the West burns up. So does the boreal forest all over the world. Somebody very cogently asked the question earlier this morning, do the models factor in all that extra smoke and CO2 from fires? They do factor in the CO2 that comes out of this. And this is part of that feedback that I mentioned earlier that helps heat the planet up more when they do this coupling. They don't yet factor in the smoke. And that's going to have to be one of the next things that they do. But the smoke does rain out. And so it's a more transient effect in the models. But it is something that we're going to have to do. But this is huge. I mean, I point out these global scenarios because none of our forestry is unrelated to the forestry that's going on everywhere else on the planet. We are living in a flat world now. We import wood, we export wood. And what happens somewhere else really affects us as well. If you look at carbon balance, the blues are areas of increased carbon in ecosystems, and the yellows are losses of carbon. And so this particular simulation, it's the same one that we looked at for fire. So notice we have increased fire in the west, and we've also got increased carbon sequestration in the west. They are both happening simultaneously. And what's going on there is that you've got a more favorable moisture regime, both increased rainfall and increased water use efficiency, but you're starting with dry ecosystems. So that's just like pouring fuel on a fire. And so you build up more woody vegetation, but it doesn't burn everywhere all at once. And so where it burns up, it burns, but it's growing like bandit everywhere else. So it's growing everywhere all the time, but it's burning more selectively in locations. So you do get both things happening. And it also shows that there are areas around the world where the boreal forest in blue is expanding north, but losing carbon at the southern edge. Same thing here. We're seeing where the boreal forest is gaining carbon as it goes north, but it loses it on the trailing edge, particularly the trailing edges that abut grasslands. If those trailing edges of the boreal forest abut temperate forest, it's a little more complicated response. This is vegetation change, vegetation distribution change. And so what I've chosen to map here is simply the vegetation that it changed to. You remember I showed you a map of vegetation as it's simulated today, and this is that map showing what it's changed to. For example, here's the southern edge of the boreal forest in brown, which is shrubland. So it says, all right, that big, huge chunk of boreal forest turned into shrubland. And we saw how it burned up under previous slides. So we see a lot of that. We see a lot of fire and change in the tropics and all over the planet. Now this is at a very high level of vegetation classification. It's a very upper level physiognomic classification. If you're familiar with the national vegetation classification system that's being built, it's all physiognomic on the top half and then trees out to species associations. If you dropped lower down into this thing, the lower you dropped, the more color would show up on this map, to the point where virtually no place on the map is without change. And so everything changes in these models. This is just showing you, can they keep up with migration? It's asking the question, how fast do the species need to move, and where is it that they need to move in order to keep up with the rate of change? And it's essentially saying that the fastest rates are where the planet gets warmest, and that's up in the boreal forest region. And that 17%, this is a bar graph of how much of the surface area of the Earth is at a certain rate of speed, and 17% under this simulation, actually it's an amalgam of 17 different simulations, 17% of the Earth's surface is faster than any rates observed in the fossil record. And so the bottom line is trees won't keep up. At least a lot of trees won't keep up. But we're going to come back to migration in a minute. So let's move down to regional assessment. I said we can play with games with fire. After World War II, fire suppression really kicked in with a vengeance. Guys took their equipment, went out in the woods, and started putting out fires like mad. And without going into the simulations that show it very well, what effectively we've determined empirically is that it appears as though we've been able to knock fires back to about 1/8 of the area that they would have been without fire suppression. So we'd have 8 times as much area of fire on average in the United States without fire suppression. So what we can do is run the model with fire suppression and without fire suppression. And when we have a fire, we calculate the area, we just say, well, all right, we're only going to let 1/8 of that area burn. And we leave all the rest of the biomass on the ground, and then we take the difference at the end of the run between those two runs and ask, where is all that extra biomass? So here's our hypothesis of where that biomass is in absolute units of kilograms per square meter. And not surprisingly, it's up in the big productive woods of the Northwest and Northern Rockies. But if you take the same data and reproject it in terms of percent increase in biomass relative to what it would be without any fire suppression, then it shifts the gravity of the map into the interior dry ecosystems. And you see that much of the interior west is slated or shown to have likely doubled or more than doubled in carbon density in the last 50 years as a direct result of fire suppression. So what does that mean? Well, here's a slide from Prineville, Oregon in 1910, and you see there aren't many trees here, and here it is in 1991. Now, this is due to a lot of reasons, not least of which is fire suppression, but also grazing and building fences. They use this wood for fence posts. And so there are a lot of reasons, but the climate has also become very favorable for the expansion of woody vegetation. And so putting out fires has just let the climate have its way with the vegetation. Now, another thing about this vegetation, and most vegetation, and in fact one of the fundamental principles behind these models that allows them to work, is that vegetation tends to grow up until it finds the maximum leaf area that can be supported at that site and just barely use up the available soil water. So the leaf area is like a wick. The more leaf area you have, the bigger the wick is, and the faster you pull the water out of the soil. So it naturally finds that upper limit. And if you don't have enough leaves, it'll keep growing. If you have too many, it'll die back. And now what this does then, it suggests that most ecosystems out there are naturally at a drought threshold. So all you'd have to do is lengthen the growing season, heat it up a little during the growing season, and you're going to burn up the water in the soil before the end of the growing season. Now, the other interesting thing about this is that if you leave fire in the system, fire naturally knocks the density down, and so it acts in effect as a buffer to drought stress by keeping the leaf area density below its water-limited carrying capacity. Now, here's what our model simulated in blue for fire area over the lower 48 states for the last 40 years. In red is the observed fire area, and the model does pretty well. The model decides what to burn, when to burn, how much to burn, and all the effects that it has on the ecosystems. And this is 1988 when Yellowstone went up and the model nailed Yellowstone. It also would have nailed the Corn Belt, which was part of why the Corn Belt was actually a natural prairie peninsula. But it also shows this increase in fire after that 1988 big blast, which was also a big drought. It was a massive drought in the Mississippi area. And so the model nailed this very nicely. And now this has been picked up by Westerling and others as large wildfire activity increased suddenly and dramatically in the mid-1980s. They didn't point to why. We know now that all the world's oceans undergo interdecadal patterns of climate variability, not just El Nino, La Nina, interannual patterns, but interdecadal patterns. You probably all have heard of the Pacific Decadal Oscillation. There's also an Arctic oscillation, a North Atlantic oscillation, and about 7 or 8 other oscillations that have been defined. This is just the North Atlantic oscillation, and in 1988, it popped to a positive phase of a severe magnitude and stayed there for a number of years that is unlike virtually anything, with possible exceptions back here, of anything in the last 150 years or so. This was an extraordinarily unique event. And this, in fact, appears to be what steered the jet streams into different configurations and caused the climate-driven increase in fire in the West, and drought and infestations and all kinds of things that occurred. Now, this is just, it's not a perfect simulation, but it's a simulation of how much biomass would have been consumed on average per year in the last 50 years, say, of the 20th century. And so you can't see it very well, but blue is actually burning, and then most of the burning would be over here along the interior west coast. And now this is one future simulation. So you see what's happening to the west, that there are big increases of fire in the west, and that's all due to this increased moisture, increased woody expansion that I talked about. But look at what's happening to the east. What's nailing the east is actually seeing increased rainfall and increased water use efficiency. But what's nailing the east is this business that it's at its water-limited carrying capacity. With the exception of the southeast forests, most of the eastern forests have been without fire for the last 100 years or so. And so it's always at a drought threshold. Now, again, to show that it's not just our model doing this, here's going back to this LPJ model, and the red shows decreased runoff in the eastern U.S. A lot of major decreased runoff in the eastern U.S. Some increase in the west, but modeled. This is what it does with fire. It burns up the eastern U.S. just as our model does. And it also burns up the western U.S., not unlike our model. And it also shows movement north of the boreal forest with burning along the southern fringe, just as our model does. So it's coming out fairly consistently among the models. This is using just the biogeography model, an equilibrium biogeography model, but it's looking at runoff. And so this is an average across 7 different future climate scenarios. And we use this in the last US GCRP assessment, 2000. And the green shows big increases in runoff in the west, and this is due to this increased runoff, or increased rainfall that tends to hit the west. And it also shows big decreases in the eastern United States. So the eastern United States really is on a threshold with regard to both forests and fire and water. And frankly, when we do the global simulations, it appears to be about one of the most sensitive, if not the most sensitive, large area on the entire planet. This is a simulation of vegetation distribution under current climate. It's an average for the period 61 to 90. And so these are forests, for example, in the eastern U.S., and there's sagebrush and savanna and woody vegetation in the west with fire suppression. If you look at one future scenario with no fire suppression, we still get woody expansion in the west, even without fire suppression. But look at the east. The east just burns up, turns into savannas, woodlands, and grasslands under this particular scenario. There are other scenarios where the vegetation actually expands. So there is some tipping point balance or uncertainty among the different GCMs with regard to what's going on here. You put out fires, then you can bring the east back out. In fact, you can actually change the sign on the carbon balance if you're able to control fire. But we're already maxed out on our firefighting capabilities right now, and we're talking about easily an average of 2 to 3 times the amount of fire in these future scenarios. Now, just to show this isn't way, way down the road, I picked a random grid cell in the eastern deciduous forest and asked the question, what vegetation type is being simulated over time? So it's simulating forest for the whole 20th century, and then out around 2015, a big fire hits, smacks it to savanna, it grows back to a more dense woodland, gets burnt again, goes to a grassland, and then pops back to woodland and oscillates for a while until it levels out at savanna. So that's not down the road, that's near term when some of this stuff could occur. And then this, just to get back to the west again, the brown here would be yellow pine and juniper savanna type vegetation, and that's expanding into the Great Basin sagebrush in this simulation. But as I said, this is a high level in the classification tree. Let's drop down a level to full 45 vegetation types. Now look at the west here. This is, again, this is sagebrush in gray, and this is what it looks like at a high level of classification, at a low level of classification, so more vegetation types. One of the things I want to point out, this blue area down here is almost an exact simulation of the distribution of canyon live oak, Quercus turbinella, even to a disjunct over here in California, and it indeed spreads up north in these distributions, just as Robin said it did in the Middle Holocene thermal maximum, about 250 miles or more. But it also brought with it a whole host of other Southwest and Texas vegetation and species that are that are frost intolerant. And my time's running out, but I'm almost done here. While we're on the migration bit, though, because that demands a lot of migration, what's happening here is that this frost line that's sitting on this drought, or on this elevation scarp separating the two desert systems, pops up over the top like a threshold, lets loose the floodgates, and away they go. But can they keep up? This is a simulation by Louis Iverson of Pinus virginiana in the east. This is observed, and this is his simulation. And under one future climate, he shows in the yellow, this is how far it could go. But if he constrains that to a more realistic migration rate, then it only winds up in this little part here. So the story here is that species are going to move out there at different rates, and the fastest ones are going to be your early successional weedy species, the ones that move around most readily and are also aggressive competitors, early establishers, and they're going to pop down into the ranges of your native endemics and threatened and endangered species that don't migrate very rapidly. So you have the whole spectrum of migration rates, and they're all just going to move out there and stretch out, and that is going to cause the mixing of your vegetation species. Now, just briefly looking at a landscape, this is looking at the San Francisco peaks, pinyon juniper woodlands in May. Here it is 4 months later. You guys all know about this. So there's just massive dieback. There's also an Ips beetle involved in this, but it was triggered by drought stress. It's a threshold phenomenon that had to do a combination of drought and also this ecosystem had hit its water-limited leaf area carrying capacity. And so then just briefly, Linda showed some of these slides already. We've done some simulations for the state of California, and left is simulated current distribution right is future distribution of vegetation. So we can do these assessments at a statewide level. And the interesting thing here is that even looking across different scenarios, when we get down to really topographically explicit simulations, we see signatures of response that occur across different scenarios. So there's a lot of similarity in these areas in red that show increased fire. Yes, there are also dissimilarities. There's less fire on the lower coast here, more fire in these two simulations. But look at these other spatial patterns of increased fire. So we can begin to pinpoint areas on the landscape that would be more or less sensitive to change than other areas. And then just to again underscore the uncertainty of near-term forecasting for these California simulations, this is biomass consumed over the 21st century, 2000 to 2100. And I simply want to emphasize the strong interdecadal signature here, and that if you look at different scenarios, some of them go up in biomass consumed or area burned, some of them go down over the same decade. And so that's the level of uncertainty that we have to deal with. Some colleagues of mine, Steve Running and Dan Faegre, did a study at Glacier National Park where they ran a simulation of vegetation change. You're looking at vegetation change and glacier change now over the 20th century, and this is what it would look like as you begin moving into the 21st century. And you can see, obviously, the green as grasses beginning to come into the valley floor. You've lost the glaciers by 2030 in this simulation. And the grasses start marching up the slopes by 2060. And so there's very dramatic change being simulated for this landscape. And we're on a quest in a West-wide climate initiative among all three stations to drill down and begin doing that kind of landscape level analysis and simulations on your favorite forests, wherever they happen to be. As Linda pointed out, we also need to change the toolbox. Most of the quantitative tools that we use, FVS, TELSA, VDDT, they don't know about climate because they're constructed around the worldview that the future will echo the past. And so we need to rebuild these things. We'll take baby steps first and try and tweak knobs in them to mimic some of these future scenarios. But they need to be rebuilt. And we're going to have some fairly serious sit-down and discussions with the managers, between the managers and the scientists, to kind of come to grips on what the real needs are and how best to meet them. And this is going to include a lot of socioeconomic factors in this as well. And so just very briefly then, I wanted a couple of personal musings of mine. And that is, again, as I've said, the future is uncertain. It will not echo the past. We are now in a condition of managing change per se. We need to recognize that and ask, what do we do to manage change? Well, that may be, for example, to improve the resilience of the ecosystems to rapid change, perhaps keep the forest density below the water limited carrying capacity if we can do that. Most of these ecosystems find that maximum leaf area within 5 to 15 or 20 years after a disturbance, and then that leaf area just stays constant while the forest underneath it changes and thins and grows bigger stems. And instead of planting homogeneous plantations, we may want to plant diversity and let the landscape find its own future. We've talked about adaptive management. I like to think about adaptive landscapes. What can we do to build landscapes that can find their own future? And then fire and carbon and other policies may be at cross purposes. If we manage for carbon sequestration, we may load up carbon on the ecosystems and find that we're draining the water out of the streams, or that we're also setting it to be susceptible to a catastrophic fire. And so, two ways to think about carbon sequestration. Normally we think about sequestration as a bank, that is, how much carbon can you put into that ground and maintain over time, even through harvest and disturbance periods? What's the average maximum you can maintain that carbon level? Well, that's one way to think about it. Another way to think about carbon on the landscape is to think of it as a carbon pump. That is, the vegetation pulls CO2 out of the atmosphere, turns it into wood, we pull it out and turn it into long-lived products or directly into energy, either electricity that we pump back into the grid or even ethanol. But this means a whole new infrastructure with little biomass plants, perhaps, dotted all over the West, so you don't have to truck the wood very far, and new kinds of markets for composite materials. So that's about it.